In 1925, a man named Frederick Rensselaer stood in a factory in Hartford, Connecticut with a vision that would change the world. He believed that the best airplane could only be designed around the best engine. From that conviction, Pratt and Whitney Aircraft Company was born, and for nearly a century it would dominate the skies, powering everything from World War II fighters to the sleek jetliners that connected continents. By the early 2000s, Pratt and Whitney had survived wars, recessions, and fierce competition, but they faced a new challenge, one that threatened their very existence. The jet engine market had become a battleground, and Pratt and Whitney was losing ground to rivals like General Electric and CFM International. Airlines demanded engines that burned less fuel, made less noise, and cost less to operate. The company needed a breakthrough, a technological leap that would reclaim their throne. What they came up with was brilliant, a revolutionary design called the Geared Turbofan. It promised to save airlines millions, cut emissions dramatically, and usher in a new era of quiet, efficient flight. They called it the PW1000G, and it represented a $10 billion bet on the future of aviation. But hidden within this engineering marvel was a microscopic flaw, a contamination so small you could barely see it, yet powerful enough to ground hundreds of aircraft, push airlines into bankruptcy, and turn Pratt and Whitney's greatest triumph into its most devastating crisis. To understand how everything went so catastrophically wrong, we need to go back to where it all began. By the early 2000s, Pratt and Whitney was facing an existential crisis. The company that had once powered half the aircraft in World War II, that had created the legendary J-57 engine for the B-52 bomber, and the commercial jets that started the jet age, was watching its market share erode year by year. Airlines were choosing engines from CFM International, a joint venture between General Electric and Francis Safran. Their CFM56 engine had become the workhorse of commercial aviation, powering thousands of Boeing 737s and Airbus A320 aircraft. Pratt and Whitney desperately needed to innovate, but jet engine technology had reached a plateau. Conventional turbofans all worked the same way. A massive fan at the front sucked in air, most of which bypassed the engine core to provide thrust, while a smaller portion went through the compressor, combustion chamber, and turbine. The problem was physics. In a traditional turbofan, a single shaft connected the fan to the low-pressure turbine, forcing them to spin at the same speed. But here's the catch. The fan worked most efficiently at lower speeds, while the turbine needed to spin much faster. Engineers were trapped in a compromise, unable to optimize both components simultaneously. Pratt and Whitney's solution was audacious. What if you could disconnect the fan from the turbine using a gearbox, allowing each to spin at its optimal speed? The concept wasn't entirely new. Small business jet engines had used these geared fans for decades, but no one had ever successfully scaled the technology to the massive engines needed for commercial airliners. The engineering challenges were staggering. You'd need a gearbox capable of transmitting 30,000 horsepower, more power than 30 Formula One race cars combined, while weighing as little as possible and operating flawlessly for tens of thousands of flight hours without maintenance. Most engineers thought it was impossible. General Electric and CFM looked at geared turbofan technology and walked away, citing concerns about weight and reliability. They believed the risks outweighed the benefits. But Pratt and Whitney saw an opportunity. Led by a team of brilliant engineers, they spent years developing what they called the fan drive gear system, a planetary gearbox with only 7 moving parts that could reduce the fan speed by a ratio of 3:1. This meant the fan could spin at a leisurely 4,000 to 5,000 revolutions per minute, while the low-pressure turbine screamed along at 12,000 to 15,000 RPM, and the high-pressure core reached over 20,000 RPM. The benefits were extraordinary. With the fan spinning slower, you could make it larger without the tips going supersonic, which meant you could achieve bypass ratios of 12:1 compared to 5 or 6:1 in conventional engines. More air bypassing the core meant dramatically better fuel efficiency. The slower fan tips also produced far less noise. Pratt and Whitney promised that the geared turbofan would deliver 16% better fuel efficiency, 75% reduction in noise footprint, and 50% lower nitrogen oxide emissions compared to previous generation engines. For airlines operating off razor-thin margins where fuel represented their single largest operating cost, these numbers were revolutionary. A single aircraft could save over $1 million in fuel costs over its lifetime. Multiply that across a fleet, and you're talking about hundreds of millions of dollars in savings. The environmental benefits were equally compelling. Each aircraft would reduce carbon emissions by 3,000 tons per year. In an industry increasingly pressured to address its environmental impact, the geared turbofan seemed like the answer everyone had been waiting for. The first major customer came in 2006. Bombardier announced it would use Pratt and Whitney's new geared turbofan exclusively for its revolutionary C-Series airliner, later renamed the Airbus A220. Then came the big one. In 2010, Airbus announced that the PW1000G would be one of two engine options for the A320neo family, competing directly against CFM's new LEAP engine. This was the holy grail of commercial aviation. Orders poured in. Embraer selected the geared turbofan for its E-Jet E2 regional jets. Airlines like JetBlue, Spirit, Wizz Air, Indigo and Go First committed to hundreds of aircraft. By the time the first engines entered service in 2016, Pratt and Whitney had spent $10 billion on development. It was the biggest bet in the company's history. The first PW1000G engines entered service in 2013 on the Bombardier C-Series. Pilots loved the quiet operation and smooth performance. Airlines appreciated the fuel savings. The technology worked exactly as promised, at least initially. But as more aircraft entered service and accumulated flight hours, cracks began to appear, literally. Airlines started reporting unexpected engine issues. Some engines were requiring maintenance far earlier than anticipated. There were problems with the combustor liners, issues with turbine blades, and troubling vibrations in certain operating conditions. Pratt and Whitney scrambled to address each issue, releasing software updates, component redesigns, and new maintenance procedures. The problem seemed manageable, typical teething issues for a new engine program. But in July 2023, everything changed. Pratt and Whitney made a stunning announcement. They were ordering a massive recall affecting potentially 1,200 engines, roughly 40% of the entire PW1000G fleet. The reason? Contaminated powdered metal. Here's where the story gets truly shocking. Modern jet engines use incredibly advanced materials to withstand the extreme temperatures and stresses inside the engine core. Some critical components, including high-pressure turbine discs, are manufactured using a process called powder metallurgy. Instead of casting or forging solid metal, manufacturers create a fine metal powder, compress it into shape, and then heat it until the particles fuse together. This process allows for precise control over the material's properties and can create components stronger and lighter than conventional manufacturing methods. But the process has one critical requirement. The metal powder must be absolutely pure. Even microscopic contamination can create weak points in the final component. And somehow, somewhere in Pratt and Whitney's supply chain, contaminated powder made it into production. Between late 2015 and mid-2021, an unknown quantity of PW1000G engines were built with compromised components. The contamination was so small it was nearly invisible, but under the immense stresses of operating inside a jet engine, these impurities became cracks. The cracks grew with each flight cycle, weakening critical rotating components spinning at thousands of RPM. The affected parts included the high-pressure turbine first and second stage hubs, the high-pressure turbine second stage disc, and the high-pressure compressor 8th stage disc. These weren't peripheral components, these were the heart of the engine, parts that if they failed catastrophically, could send turbine blades shooting through the engine cowling or even the fuselage. The safety implications were terrifying. Pratt and Whitney had no choice but to order immediate inspections of every potentially affected engine. But here's where the crisis became a catastrophe. The inspections weren't simple. You couldn't just look at the engine while it was attached to the aircraft. The entire engine had to be removed, shipped to a specialized maintenance facility, completely disassembled, and thoroughly inspected using advanced imaging techniques. If contaminated parts were found, they had to be replaced with new components. The process took between 250 and 300 days, nearly a year per engine. Think about what that means. An airline with 80 aircraft, each with 2 engines, suddenly learned that 40 or 50 or 60 of those engines might need to be removed from service for up to a year. With spare engines in short supply and Pratt and Whitney's production capacity already stretched thin, building new engines for aircraft manufacturers, airlines faced an impossible situation. They had to park perfectly good aircraft because the engines were sitting in maintenance shops halfway around the world. The impact was immediate and devastating. By early 2024, over 600 aircraft were sitting idle in storage, representing nearly 1/3 of the entire geared turbofan fleet. Compare that to CFM's competing LEAP engine, where fewer than 90 aircraft were in storage, less than 3% of that fleet. The disparity was staggering and damning. Some airlines were hit harder than others. Low-cost carriers like Spirit Airlines, Wizz Air, Go First and Indigo had bet heavily on the fuel-efficient geared turbofan to keep their operating costs competitive. Now they watched, helplessly as their fleets dwindled. Spirit Airlines, once one of America's most aggressive budget carriers, had planned for 7 aircraft to be grounded through the end of 2023. Instead, they had an average of 20 grounded at any given time in 2024, with projections suggesting that the number could triple. The financial pressure was crushing. Spirit was burning through cash, unable to fly enough routes to cover its fixed costs. The company tried everything, negotiating compensation packages with Pratt and Whitney, seeking emergency financing, cutting routes and laying off staff. Nothing worked. In November 2024, Spirit filed for Chapter 11 bankruptcy protection, citing the Pratt and Whitney engine crisis as a major factor. They emerged from bankruptcy in March 2025, touting a lighter debt load and a sustainable path forward. But the reprieve lasted only months. In August 2025, Spirit filed for bankruptcy, again, this time facing an even more dire situation. Lease agreements were terminated, creditors were circling, and the airline's very survival hung in the balance. Across the world in India, the story was even more dramatic. Go First, an Indian budget airline, operated a fleet almost entirely dependent on Airbus A320neo aircraft powered by PW1000G engines. When the recall hit, Go First's operation collapsed almost overnight. The airline filed for bankruptcy in March 2023, explicitly blaming Pratt and Whitney for the crisis. In court filings, Go First claimed that Pratt and Whitney had failed to provide adequate spare engines as required by their agreements. Pratt and Whitney fired back, arguing that Go First had no right to demand new engines because the aircraft leases had been terminated due to Go First's own financial mismanagement. The legal battle became nasty, with billions of dollars at stake. But the arguments didn't matter to the thousands of employees who lost their jobs or the passengers left stranded when Go First suspended all operations. By mid-2023, the airline was finished, another casualty of the geared turbofan crisis. Other airlines faced similar nightmares. JetBlue expected to have an average of 11 A320neo family jets grounded at any time throughout 2024. Wizz Air, Europe's fastest-growing ultra-low-cost carrier, had dozens of aircraft parked. Indigo, India's largest airline, watched its ambitious expansion plans evaporate as more and more aircraft sat idle. Even Air Baltic, which operated a small fleet of A220 aircraft, had half its planes grounded at one point. The human cost was staggering. Tens of thousands of jobs disappeared. Pilots who had trained for years found themselves furloughed. Flight attendants, mechanics, and ground crew joined unemployment lines. Small airports that depended on these budget carriers for connectivity saw service reduced or eliminated entirely. And passengers? They faced higher fares as competition decreased, fewer flight options, and the constant uncertainty of whether their airline would survive long enough to honour their tickets. But the crisis wasn't just about the airlines. Pratt and Whitney itself was bleeding. The company set aside a $3 billion charge to cover recall costs, but that was just the beginning. They had to compensate airlines for lost revenue, provide interim credits, and somehow ramp up both production of new engines for aircraft manufacturers and maintenance capacity for the recall. The company's reputation, built over nearly a century of engineering excellence, lay in tatters. Parent company RTX, formerly Raytheon Technologies, saw its stock price hammered as investors worried about the long-term implications. The recall was initially expected to peak in early 2024 and gradually wind down. Instead, the problem kept growing. By late 2025, over 835 aircraft were in storage, up from 748 just months earlier. The stored fleet represented 33% of all geared turbofan-powered aircraft, and industry analysts projected the crisis would extend through the end of the decade. How could this happen? How could a company with Pratt and Whitney's pedigree allow the contaminated powder to enter production for 6 years without detection? The answers point to a perfect storm of factors. The push to compete had created intense pressure to bring the geared turbofan to market quickly. Pratt and Whitney was burning billions of pounds, while CFM's LEAP engine was winning orders. Every delay meant lost market share. The powder metallurgy process itself was relatively new at this scale for jet engines. While proven in other industries, applying it to extreme conditions inside a high-pressure turbine pushed the boundaries of materials science. Quality control procedures that worked for conventional manufacturing might not have been adequate for this new process. Supply chain complexity also played a role. Modern jet engines aren't built by a single company. Components come from suppliers around the world, each with their own manufacturing processes. If contamination occurred at a supplier's facility, it might not be detected until components were installed in finished engines, and testing has limits. You can't test every component to destruction. Instead, manufacturers rely on statistical sampling, testing a percentage of parts and assuming the rest meet standards. If contamination varied from batch to batch, it could easily slip through sampling-based quality control. There's also the uncomfortable reality that Pratt and Whitney was under enormous financial pressure from stakeholders in the market. The company had spent $10 billion developing the geared turbofan. It needed to start recouping that massive investment, which meant getting engines out the door and into service as quickly as possible. Did that pressure lead to shortcuts or overlooked warning signs? We may never know the full story. What we do know is that the consequences have been catastrophic, not just for Pratt and Whitney, but for the entire commercial aviation industry. So where do things stand now? Pratt and Whitney insists it has turned the corner. The company has expanded its maintenance capacity by 40%. It's introduced the GTF Advantage, an upgraded PW1000G with improved durability, which began production in late 2025. The company is also rolling out a Hot Section Plus upgrade package, replacing 35 components in existing engines with improved versions. These upgrades are supposed to address the durability issues. The company projects that by the end of 2026, it will complete the bulk of the recall work. Full recovery should come by the end of the decade. But airlines have learned painful lessons about trust. When United Airlines, a major Pratt and Whitney customer historically, placed an order for Airbus A321neo aircraft, they shocked the industry by selecting Pratt and Whitney engines even after watching the recall unfold. Some analysts saw it as a vote of confidence, a sign that the problems had been fixed. Others saw it as a calculated gamble, betting that Pratt and Whitney's desperation to rebuild its reputation would result in better pricing and support. Time will tell which interpretation is correct. For the airline still suffering through the crisis, the pain continues. As of late 2025, Pratt and Whitney had delivered about 1,000 new engines that year, a 6% increase from the previous year. But with over 800 aircraft still in storage and more requiring maintenance each month, it's a race against time. Spirit Airlines, after its second bankruptcy filing, reached a settlement with Pratt and Whitney affiliates for up to $140 million in compensation. The airline is now trying to restructure around a much smaller fleet, keeping only 10 to 28 A320neo aircraft while divesting the rest. It's a shadow of its former ambitions, a company that once dreamed of national domination now fighting just to survive. The broader industry has drawn its own conclusions. When Airbus and Boeing design their next generation of single-aisle aircraft, expected to enter service in the early 2030s, engine selection will be critical. Will airlines trust Pratt and Whitney's next innovation? Or will they play it safe with proven technology from CFM or Rolls-Royce? The scars from the PW1000G crisis run deep. There's a bitter irony in all of this. The geared turbofan technology itself works beautifully. When the engines are running properly, they deliver exactly what was promised. Exceptional fuel efficiency, dramatically reduced noise and lower emissions. Pilot style and passengers love the smooth, quiet operation. The engineering breakthrough was real and revolutionary. What failed wasn't the fundamental design but the execution, specifically the manufacturing quality control that allowed contaminated materials to enter production. It's a reminder that in aerospace, where safety is paramount and margins for error are measured in microns, excellence in design means nothing without perfection in manufacturing. Every component must be flawless because a single failure at 30,000 feet can have catastrophic consequences. The PW1000G crisis also highlights a deeper problem in modern aviation. As engines become more advanced, more efficient, and more complex, the consequences of failure become more severe. We've created systems so sophisticated that diagnosing and repairing problems requires months of work by highly trained specialists using equipment found in only a handful of facilities worldwide. When something goes wrong, you can't just swap in a spare part and keep flying. You ground the aircraft, remove engines weighing several tons, ship them across continents, and wait while teams of engineers painstakingly inspect and rebuild them. This vulnerability is baked into the industry's economics. Airlines operate on thin margins and can't afford to keep large inventories of spare engines sitting idle. Manufacturers focus on maximizing production of new engines for new aircraft, rather than building up reserves for potential recalls. When a crisis hits, the system has no slack, no buffer to absorb the shock. And what about the passengers, the people who just wanted to get from point A to point B? They paid the price in higher fares as competition decreased, in cancelled flights and disrupted travel plans, and in the uncertainty of whether their airline would still exist by the time their vacation arrived. They became collateral damage in a drama of engineering ambition, manufacturing failure, and corporate survival. Looking back, the warning signs were there. The early reliability issues, the unexpected maintenance requirements, the software patches and component redesigns all pointed to an engine program struggling with teething problems, but no one expected contaminated powder metal. No one imagined a microscopic impurity could ground a third of the fleet and push multiple airlines toward bankruptcy. That's the terrifying thing about manufacturing at this scale and complexity. You can do everything right 99.9% of the time and still end up with a disaster. As we move forward, the aviation industry faces hard questions. Should manufacturers be allowed to bring revolutionary new technologies to market so quickly, or should regulatory oversight be strengthened to catch quality control failures before they become crises? How can airlines protect themselves from supplier failures when they're locked into long-term commitments for aircraft and engines? What's the right balance between innovation and reliability in an industry where both are essential? Pratt and Whitney is fighting for its future, working around the clock to repair its engines and its reputation. The company that Frederick Rentschler founded in 1925 with a belief in engineering excellence now faces the consequences of a failure in that very principle. They'll survive. Major aerospace companies always do. They're too important, too embedded in the industrial and military complex to simply disappear. But the Pratt and Whitney that emerges from this crisis will be different. Scarred by the experience, more cautious, more focused on quality control, and forever aware that in aviation, trust once lost is almost impossible to fully regain. For Spirit Airlines, Go First and the other carriers pushed to the brink, there may be no happy ending. Some will emerge smaller and weaker, others won't emerge at all. Their stories serve as cautionary tales about the risks of betting everything on a single technology or supplier. And for the engineers at Pratt and Whitney who designed the geared turbofan, who believed they were creating the future of aviation, the PW1000G crisis must feel like a tragedy. Their revolutionary design worked. The technology was sound. But somewhere in the complex global supply chain that turns raw materials into precision components, something went wrong. Contaminated powder, invisible to the naked eye, defeated a $10 billion engineering masterpiece. That's the lesson here. In the relentless pursuit of innovation, in the race to build engines that are lighter, more efficient, and more powerful, we've created systems of staggering complexity. And with that complexity comes fragility. A single point of failure, a batch of contaminated powder, can cascade through the entire system, grounding hundreds of aircraft and costing billions of dollars. The rise and fall of Pratt and Whitney's geared turbofan is a story about ambition and innovation, about technological triumph undermined by manufacturing failure. It's about the unforgiving nature of aerospace engineering, where excellence is expected and anything less can be catastrophic. Most of all, it's a reminder that even the mightiest can fall, that a company with nearly a century of aviation dominance can see its reputation shattered by impurities measured in parts per million. The engines will eventually be fixed. Airlines will rebuild their fleets. Pratt and Whitney will recover. But the PW1000G crisis will be studied for decades as a case study in how brilliant engineering can be undone by flawed execution, how microscopic contamination can have macro consequences, and how a $10 billion bet on the future can turn into a nightmare that reshapes an entire industry. The skies will keep flying, but they'll never quite forget the engine that promised to revolutionize aviation and instead became a cautionary tale about perils of pushing technology too far, too fast, without the quality controls to ensure that innovation doesn't come at the cost of reliability.